Hello, could you please close the door? Although, I guess the rest will come in like 5 minutes or whatever. Good, hello, good morning. So the topic today is to finish what we started last time. So we wanted to discuss the complex form of the Fourier series because, as I said previously, the complex notation is kind of the major notation that you find in the technical literature, especially then also with regards to MR imaging. And yeah, that's then what we want to do today. First, to rewrite the Fourier series from its real form in the complex form. And once we're done with that, we actually rewrite it again in the so-called polar form, which allows us to give some interpretation of the coefficients, especially, or to the complex coefficients that we will establish now. And then we're actually, after that, we're actually done with the Fourier series, and we can finally discuss the Fourier transform. So this transform from a function in the time or space domain to the frequency domain, what we wanted to do all along, but it needs a little bit of preparation in terms of the series. So the where we start is essentially that we have our function, our real valued our univariate real-valued function that we established is periodic with period t, and for which we also established that we can rewrite or express, let's say, or represent this function in terms of its real Fourier series, which at the end of last section or last session we rewrote as follows. So we abbreviated a little bit the input arguments to the sine and the cosine function so that we don't have to write that much. So that was our latest way to write it, where this omega 0 was 2 pi divided by the period of the function. So this is where we left off our formulation of the real valued Fourier series. And then last time what we were mainly concerned with was obviously complex numbers, so that you get a feeling for what those are. And as I said, the most important thing that, well, it doesn't really follow from that, the most important thing that we need from this whole complex of complex numbers are the Euler formulas, and specifically this first Euler formula, where you have this exponential function with the imaginary unit times x equaling or being equal to cosine of x plus the imaginary unit times the sine of x. So this is where we spent most of the last session on to discuss why this holds. And as you may remember, this holds because of the series definitions of the exponential, the cosine, and the sine function. And then finally we, because I realized that I wasn't able to discuss the complex series anymore, we discussed a little bit these two additional ways to express, using Euler's formulas, the cosine and sine function. And these are these equalities. So the cosine as the sum of two complex exponentials divided by 2, and the sine almost the same, not a minus here. Here a minus and there a minus, and divided by 2i. So this is essentially, in a nutshell, so this latter part here what we did last week, and this is what we did all the weeks before, or a few weeks before. So, is there anything left with regards to that is open?
Yeah, one question regarding the omega.
Mm-hmm.
It's 2 pi divided by t, but like in the context of cosine and sine, t would be 2 pi, wouldn't it? So wouldn't omega be 1?
Yes, but so this t refers to this function, so this arbitrary function, so that it's not a cosine or a sine, so that is, I don't know, let's say something like this, some very weird function. So, and this has this period t, and then what you put in here, so what it used to be was that it's cosine 2 pi k divided by t x. So this used to be the input to the cosine and the sine function, and we just re-expressed that in terms of 2 pi divided by t times k, and this 2 pi divided by t being omega 0. The thing is, yes, the cosine and the sine function are periodic, but the t refers to the period of the function that we're trying to re-express in terms of the sinusoidal and cosine functions. And then, yeah, I mean, the cosine and the sine themselves, they remain periodic. So when you have 2 pi, for some reason, that this k omega 0 times x is 0, for example, because x is 0, and then k omega 0 is 2 pi and x is 1, then yes, you get the same number, but these periodicities refer to different things. But why is it bothering you?
No, I was just interested in that because I wanted to figure out like how to imagine every single letter, like what would be changing if I change something in this letter.
So what changes is that so if you change the k, and this is the important thing. So there are the two most important things in terms of changing are actually the k, because this k runs from 1 to infinity, and this indexes all the different frequencies, right? So if k goes up, then the frequency that you put into cosine and sine goes higher and higher. Yeah? So the k indexes frequencies. The x, of course, indexes the argument of the original function. So what you would have if this is the original function on the x-axis. And the omega 0 is just the radial frequency that you have if k is 1. So that's the base frequency, if you wish. So if k is 1, then omega 0 is the frequency that refers to that case. Yeah. So if you put in k1, then you have omega 0 times x. Remember, radial frequency is this mu x from one of the first sessions. So then you are in this case of the base frequency. If k is then 2, because you go up the sum, then you're at double this base frequency. And this base frequency is defined in terms of 2 pi divided by t. So if you have a longer period, then so if t gets larger, then your base frequency gets smaller. So these are the connections between these letters.
Okay. So in this context, omega now isn't the circular frequency anymore, but the radial frequency.
Exactly. No, it's not actually the radial frequency. The radial frequency is k times omega 0. Omega 0 is just, I could have called it differently, but that's how it's typically called. It's just this. So you should not, because sometimes the same letters refer to different things, and then it's more important what they refer to rather than what the omega referred to on an earlier occasion. Yeah. Anything else about Euler's formulas or something? No. Good. So everybody is somewhat happy with that. So the point now is that in principle we are already done. We are not done at all. We're just starting, but in principle, we can express a function that is well behaved in the sense that it fulfills the Dirichlet conditions, as we discussed, so that it's periodic. We can express that as an infinite sum of cosine and sine components of different frequencies and different amplitudes. And that's fine, and like I said last time, the intuition also doesn't change. It's the cosine and sine components, so with different frequencies that play a role, but now we re-express that in terms of complex exponentials, so in terms of these kind of things, because it's, in a way, it's a little bit more compact, and mathematics likes to be quite compact to not have to write too much, and then it's just everywhere in the technical literature. So if the technical literature would be different, so that the Fourier transform would be defined in terms of cosine and sine, then we wouldn't have to bother with this, but it's not. So the Fourier transform itself is defined in terms of the complex exponential, and hence we need to talk about it. Yeah? It's a little bit now just little calculations rewriting, so it's not conceptually horribly complex or something, but on the other hand, I think it's quite important to really see these equivalences, to not always wonder until the rest of your life in cognitive neuroscience or in general what it's about, this complex exponential, because that is just confusing and it wouldn't be clear. And as I said, if you do a Fourier transform, for example, in MATLAB, has anyone done a Fourier transform in MATLAB or in some other programming language? Then did you get complex numbers out of them?
Yes.
Yes, see? So I'm not the only one who says that there are complex numbers coming out of Fourier transforms, so it makes sense to talk about them. One could also write this Fourier transform algorithms different, so that not complex numbers come out of them, but that's not the case. Good. So at least two people tell you that it's meaningful what we are doing here. Good, and now let's essentially just do it, or maybe we can actually leave this on for a little bit, because we will start, well, I will write it up again. So we basically just reformulate things now to come up with a more compact representation, but I want to go a little bit go a little bit slowly about this, so that you feel happy that it's just that there is no magic, there are no tricks, or I mean there are tricks, but there is no magic, so that it's fairly natural. It's just putting in substitutions for other things. So again, we start with the real Fourier series. Where we have what I just wrote above, k, which indexes increasing frequency, omega 0, so the base frequency, and x, which is the input argument to the function, and same thing, bk sine k omega 0 x. And then the first step is that we use these equalities, cos x eix plus e minus x minus ix divided by 2, and then by 2i, and replace the cosine and the sine function. So remember again, these equalities here, they follow directly from Euler's formula, and the first one we actually saw, the other one is in the script, so you can you have the little proof there. It's 549 in my version, but you have it, right? Everybody is happy seeing it, so we don't go over that. So now we just replace the cosine and the sine, and that's what we do. So we get this So we still have a sum from 1 to infinity. We still have our AK coefficients. Remember that we also have the formulas for these AK, BK, and A0. And now we put in for cosine this. So we only need to account for the fact that we actually, our x here is actually k omega 0 x here, because this is, so you can, this x, so this whole thing is x if you put in k omega 0 x on this side, yeah? So don't get confused by the x, it's just the input argument. So we get e I k omega 0 x plus e minus I k omega 0 x, and we divide it by 2 because that's what this equality says, plus maybe I write directly underneath, plus bk, and now we replace the sign and get a I k omega 0 x minus a minus I k omega 0 x divided by 2I. So far, so good. Happy so far? Questions so far? Okay, we just use these equalities. And now we do not really tricks, but do a little bit so that we get to where we want to get. So our A0 is still around, our sum is still around, and the only thing that we do is that we have a product here, so we we might as well put 1/2 before this sum, or divide the AK by 2. Maybe because I put in this extra step, for the moment I really do minimum stuff on this, so we just take the 1/2 in front of it. Where we do a little bit more is here. So we multiply our bk with I divided by I, so 1, so nothing happens, and take also here the 2I in front of the sum. So that's all just minimal manipulation of anything, so that doesn't really change anything. And the reason we do that is just so that we get in the end to where we want to get. So nothing has changed. Is there a question?
Yeah, why this I are divided by I?
Yeah, it's just a trick so that we get where we want to get, but the it's just 1. Yeah. So.
But you just filled it in now.
Yeah. Yeah, it's just to do this reformulation in terms of, or into the complex Fourier series. This is, I mean, we could, I'm doing this here a little bit in kind of the physics way, so we start and then we manipulate here and then, in the end we get to something. We could have also done it in theorem form, so that I first give you the complex Fourier series and then provide a proof. So essentially we're doing the proof now, and in the proof you always do little tricks so that the proof works. But these little tricks, obviously, they don't change anything. So the expression is the same. A 1 is just replaced by I divided by I. Okay. Then we go on and check our cell phone, and then we smartphone, and then we go take the AK, take the 1/2 and divide AK by 2. So we just take the 1/2 out of the bracket here. Also doesn't is not something that changes anything. nothing of this changes anything because it's all equalities. It's just getting us closer to our complex form. And what we're doing with this I here in the numerator is that we multiply these complex exponentials with it, and we take, as we take the 1/2 out here, we take it out. It's just so that we get essentially, as you will see in a second, to a complex number representation, but it's all just changing the order of multiplication, so it's really nothing complex is happening here. So that means that our BK, take this 2I out of it. So there we also have an I, so we have 2I square. And in the numerator we also have an I, which we now put in. So we get into the brackets, so we get I, E, I, K, omega 0x plus I, oops, yeah, I minus I, K, omega 0x. Yeah, so again, nothing happened, we just changed the order of multiplication. Yeah? It's just equalities. And then we are almost, we are basically already there, so that we can actually do something a little bit more interesting. So, what's wrong?
Question.
Yep.
You put there plus, but shouldn't there be a minus, like in between I, E?
Yep.
Or E?
Thanks. This is why I don't recommend copying what I put on the board, because I always put typos in. Yes, it's just a minus, so it just goes on as it was. Any other typos? No. Good. And now we're just multiplying things out. I mean, one could do all of these steps a little bit different. The important thing is that we get maybe a little bit more elegant. The important thing is that we get to where we are getting, and that we understand each step. That's what I'm trying here. So here we now have to pay a little bit attention. So we have here an I square, which is what? That's -1. So we change the sign here. So this is divided by -1. So we get a minus sign. So we get BK divided by 2 with a minus in front. And divided by 2. And here we have I, A, K, omega 0x, and now we are also resolving the bracket, so we have a minus in front of this here, so we have minus bracket A minus B, so you know that if there's a minus in front of brackets, the signs inside the bracket are reversed, so we get this, and yeah, our I, we can leave it there for the moment. So we have I, E minus I, K, 0x. One thing which is also helpful is that we put this I here, here, and it's a little bit easier to see. So just again changing the order of multiplication. Same for this I. So, and now we get in like 4 steps to a representation that yeah, is almost where we want to get. So you might realize that we have now certain things here. So we have exponentials with an I, K, and we have exponentials with a minus I, K. Is there a question? Or?
Not really. I was just wondering how far we have to be able to prove those things ourselves. I mean, it's clear that it's easier to understand, it helps understanding where we get the formulas from, but maybe for the exam, do we have to be able to prove anything?
No. So with respect to the exam, if this is what you get worried about now, is I mean, there are these study questions in the script, right? And if you look into them, they never ask for reproducing proofs in kinds of formal ways. They sometimes ask for formulas because this is knowledge, so one needs to learn this. Sometimes they ask about the ideas of how things come along. I don't think there's a question about this because this is not really much idea-driven. When we derive the BK and the AK coefficients, where we use the trigonomic orthogonality properties and so on. So I think there I might ask for the general idea of how to get there, but this is just rewriting with a little bit of tricks. So no. Like I said, the proofs, it makes sense to remember tricks, but not necessarily, not the details. And the important thing, yes, as you say, is in the end there will be a result, and the result is important, but if you don't understand how to get to the result, then it's really hard to understand what this result actually means. Good. So we have this positive and these negative exponentials. So essentially this one and this one, and maybe I differently, this one and this one. And as you see, or maybe not fully see, so we're reordering them now in terms of this. But then if we do that, you will see something, and that's kind of the main point. So if we now take only the positive complex exponentials, what we get is AK divided by 2 EIK omega 0 x minus IBK divided by 2 EIK omega 0 x. And you might, if you are a little bit you might see that we are getting to something like a complex number. So we have something like, I mean, we're not quite there yet, but we have something here, and then we have an I here and something else. So we're getting closer to a complex number, as we discussed them last time here. Now for the second one with the negative exponentials, we have to do something a little bit more. So here what we actually do is now is that we split the sum, and we also change the index of summation. So we start now with our k here and minus infinity and go up to minus 1. And then we need to account for that we change the index variable when we now consider our exponentials with the minus sign. So here we basically just want to write our AK, and here k goes from 1 to infinity. Now, if we want to re-express that, we need to put a minus in front of the k. So then these minuses, which we have here, they are undone, and we are back at our positive case from 1 to infinity, because we now have a minus in front of them. And the same thing applies to what we have in the exponential. So here we now put in k omega 0 x. Here we had minus I k omega 0, and here we now have k, but the k is a negative number. Yeah. So we basically here, so just to say it again, here the k is positive and goes over the integers, so 1, 2, 3, 4, 5, 6, 7, 8, and so on. That means here we have a1, 2, 3, and so on, and here we have minus I, 1, 2, and so on. And now we re-express this with negative indices. So we go k minus 1, minus 2, minus 3, but we start at minus infinity. And then to have again our positive integers, we put a minus sign in front of this and don't put a minus sign here because the minus comes in from here. Yeah, it's just a trick. Let me write the full thing and then we can discuss this. And the reason why we are doing this, and to also motivate that a little bit, because I don't do it in proof form here, the reason we are doing is that we want expressions like this everywhere, yeah? So that we then in the end can get them out of brackets. We put some brackets, but we don't necessarily. Good, yeah, so there was a question.
Yeah, I just wanted to ask, so basically it's just a trick, but the range would still be from 1 to infinity.
Yes, but the index runs from minus 1 to minus infinity, or from minus infinity to minus 1, so the way you go, which direction doesn't really matter. So yes, so the range is the same. So the range is the same, just we want essentially to get it very compact, we will have in the end just one index variable. So I have here an example, so if this is not really clear with this minus and so on. So if you, for example, if you in this version here, so let's go here. If in this version you have k equals 3, then you have a3 for this first term, a3 divided by 2 e minus I3 omega 0 x. Yeah. In this case, if you have what refers to 3 is of course minus 3. So then if you have in this scenario k being minus 3, you have a minus 3 divided by 2, which is obviously a3 divided by 2, and you're supposed to put in for k the minus 3, so you have I minus 3 omega 0 x, which is of course a3 divided by 2 e minus I3 omega 0 x. Yeah, so this is just the trick, and this is just shown here for one index. Yeah, it's just an equality. The things are the same on the left and on the right of the equality sign. Yeah. And this is just shown here again for one thing. Happy? You should. So the way this works is that you should be happy with all the steps. Good. So I assume you're happy. Otherwise, of course, it's also in the script, and you can think about it again. And if something is unclear, of course, we can also discuss that. But it's just this is just algebra. It's really not something too fancy. The benefit of this is now that we, of course, can here get the e out of the brackets, so we get to the following. So we can have 1/2, and then we can have our ak and our minus ibk. So if we multiply this by 1/2, we get this ak half and ibk half, and we get our exponential out of it. No, so that's for the first one, and for the second it's the same thing. So we can have our minus infinity minus 1. We just need to pay a little bit attention. Oops, then we need our 1/2 first. 1/2 a, no. 1/2 a minus k plus I b minus k, and again our e I k omega 0 x. And now you should really see that this is a complex number and this is a complex number if especially if the bk is not 0. If it's 0, it's just a real number, but in general it's not a real number, it's a complex number. Like we discussed last time, that complex numbers always have this form, or with the minus in front of them, and you actually, let's keep it at that. Good, and now we, based on this, we can now, we are almost there, we now redefine the coefficients. So we define a new set of coefficients which we call ck, and the reason for that is that we of course can take out unify these two complex exponentials in the next step, and to get that more into a more compact form, we define these new coefficients as follows. So ck is a minus k plus ib minus k if k is smaller than 0. Yeah. Keep in mind again that if k is smaller than 0 and you put in k here, so for example k minus 3, you get a 3. Yeah? And a 3 was a coefficient of the real Fourier series for which we have a formula. Yeah? So we have all the formulas. So these ck's are just our original formulas now re-expressed. So we know how to compute them. Yeah, because they are just given by these integrals of the function multiplied by the cosine or the sine. So that's our first case. So for k smaller than 0, we define ck as that. For k being 0, we define ck as a0, so as this one. And for k larger than 0, we define k as 1/2 a k plus I bk. Yeah, so that's now our new definition, which we can then immediately apply to what we had above. So we have our a0, which is now called c0, because we have these new definitions. And then we can replace our 1/2 ak minus I bk by our ck. Note that k is here there's a minus sign, that's why I got it wrong. Our ck, so k is positive. Our ck for positive k is defined as 1/2 ak minus ibk, which is this. And this is why there needs to be a minus sign. So we get this. And then we have our sum from where k is negative. So we have negative k, so we are in this case. And here we can replace now this by ck. Yeah, and now we have k running from minus infinity to minus 1. Then we for the c, then we have a c0 here, and we have then k going on from 1 to infinity. So the last thing that we can do is actually order things a little bit nicer. So we start with our k minus infinity to minus 1, ck, so I'm just putting the last term of the sum first now, and then I'm re-expressing the C0 as e to the power of 0. So remember that if you think about the exponential function, which we discussed in the beginning, so e to the power of 0 is 1. So if we have plus C0 here, then we can express that as plus C0 times 1, which is the same as plus C0 e to the power of 0, which is the same as e to the power of I times 0 times omega 0 x. The main thing is that we get this 0 term also into the sum in the end. Here we have from 1 to infinity c k e I k omega 0 x, and then we are actually done. So we now can write the whole thing as a single sum from minus infinity to plus infinity, if you want a plus there, or just a infinity. And then we have our ck, which are our coefficients, which if we computed the real Fourier series coefficients, we know how to compute them because we have these formulas there, times e I k omega 0 x. And this is where I wanted to get all the time. So this is where we started out in the beginning, and this is now where we ended up. So this is the complex form of the Fourier series. And the e I k omega 0 x is clear, and the ck, just remember, I'm just writing it up again so that you see that again, because we know how to compute the ak and the bk, right? We did that. Now the ck we can just compute from our ak and bk if we use these conversion formulas, and these are exactly the same definitions as above. I'm just rewriting them so that you see that again. If k is smaller than 0, we take again our a1, 2, and 3, and so on, because these are the, they come out as these, because there's an extra minus sign. For k being 0, we use our a0, and for k larger than 0, we use 1/2 ak minus I bk. Yeah? So this just is meant to remind you that if you use these formulas that we derived for ak and bk and have the real Fourier series, then you can convert based on these formulas and based on these formulas the thing into the complex form of the Fourier series. Yep.
I don't know if this is related, but k can never be a fraction between -1 to 1.
Sorry, what? K?
K can never be a fraction.
No, that's a good point. So the case, that's actually one point that is different in a way between the real and the complex form. So in the real Fourier series, k were natural numbers. Yeah. So for the real Fourier, these were natural numbers, and for the complex Fourier, they are integers, so positive and negative ganze Zahlen. So the natural numbers with their negative counterparts and 0. So this is for the complex, but it cannot. K is not a real number. When we go to Fourier transforms, then yes. Then, in a way, because you're thinking about the frequencies, then we allow for continuous representations of frequencies and correspondingly coefficients. But in the Fourier series, which is also kind of in the name, the k's are integers, because it's a sum. Yeah. Ha! Right on time. Are there other questions? Okay, so these I mean, this is like this one page in the script that we just went over. So it's a couple of steps which one can leave more implicit or make even more explicit than I wrote them up. I don't know. Might be a little bit hard to make them actually more explicit than I wrote them up. I don't know where else you want to put in steps so that it doesn't get completely annoying. But this is how you get from the real Fourier series to the complex Fourier series, and this is kind of the, I mean, it's, if you look in comparison, it's of course not much more, that more compact. So, I mean, we started out here where we have 3 terms and where we have a cosine and a sine, and now we are down here where we just have a single term, of course a sum over infinitely many terms, but in written form it's just a single term, and one form of coefficient and no sine and cosine anymore, because we have this complex exponential which derives from the Euler formula. So it's more compact, and it also implies that the coefficients are often then complex numbers. Yeah, and it's just the way that people write this. So to get a little bit more of an intuition for that, we will next look at the polar form, so that especially with the complex coefficient you can associate something with these numbers then. Yeah, but let's have a break first and start again at 9. Yeah?